This conference will now be recorded.
Hello everyone. Today the topics that we are going to discuss significant figures and related problems. Then there will be dimensional analysis, precision frequency, and different types of laws of combination. So what is significant figure? So significant figures are the meaningful digits that are required in measured or calculated quantity. So suppose we are doing any experiment and some values we are getting. So in those cases, there will be some meaningful digits. It is not that all the digits are meaningful. There will be some meaningful digits, and that are called significant figures. Now these include all those digits that are known with certainty, plus one more which is uncertain or estimated. So obviously when we are doing some experiment, there may be some manual error or instrumental error. Okay, so if we are taking 3 to 4 times reading to avoid error, then in each time the values that we are getting, it may not be exactly same. Okay, there will be some defects. So if we want to know that what is the accuracy, then the significant figure, it will help us. Fine. So it is basically what is the certainty of the value that we are getting, it gives us that idea. Now if significant figure, which is basically a number, if it is very high, then it means that uncertainty that is very small. So these two are inversely related. When significant figures are high, that means the chance of error in the value, that is low. That means uncertainty is low, but vice versa. If significant figure is very low, that means uncertainty is very high. Now, how to find out that how many significant figures are present in any measurement, whether it is calculated or measured? For that, we have to follow some rules. So here we have the rules that are required for determining the number of significant figures. If there are some zeros that are present at the end or right hand side of a number, they will be significant, but only when they are on the right side of the decimal point. Okay, so both the conditions must be fulfilled. Zero which is at the right side of the number or at the end of some number, and also they are on the right side of the decimal point. If these conditions are fulfilled, then we can say that will be considered as significant. Those zeros will be considered as significant. Here as example, we have 0.132, 0.0132 and 15.0. Now all these three values that you are seeing, the significant figure is actually 3 for all of these three. Okay, so for the first one, here this 0 is not considered because it is in the left hand side of this decimal. Okay, then for the second number, this 0, it is on the right hand side of the decimal, but it is left hand side of this number 132. So that is why this 0 will not be considered. So for the first number, the digits 132, these three are actually significant figures. That is 3 is the significant figure. For the second value, this 0 is not considered, but 132, these three will be considered. And in the last case, this 0 is now considered as significant because it is right hand side of the decimal and also right hand side of 50. So in this case, you have to consider 1, 5 and also this 0 as significant figure. So though these three numbers are absolutely different, but still all of these are having same value of significant figure, which is 3. If 0 is proceeding to first non-zero digit, they are not significant. Okay, so see, these zeros are basically indicating the position of decimal point. So in this case, we have this example 0.03. Now in this case, this 0 is not significant figure. That is this one. This 0 is not significant, but these three you have to consider. So here significant figure is basically 1. But for the other number 0.0052, though these two are all, that is, you can find some similarity. Here also after decimal we have 20 and then we have the numbers 5 and 2. but only 5 and 2 will be considered as significant. So that is why their significant figure is basically 2. So these zeros that are proceeding to first non-zero digit. So this 0, it is proceeding to first non-zero digit, which is 3. And in the second case, these two zeros, though they are right hand side of the decimal, but they are preceding this 5 2. So that is why these 0 will not be considered as significant. Only the 5 and 2, these two are significant. Now the third rule, suppose you do not have any 0 in the digit. So there will be non-zero digits only. Now when it is non-zero digits, they are actually always significant. So for example, if I am saying 285 centimeter, significant figures actually 3. If I am saying 0.25, there are 2 significant figures. Only these 2 and 5, not 0. So you have to always consider any non-zero digits if it is present, whether 0 is there or not. But if it is non-zero, we have to consider it as significant figure. So these are the rules. Okay. And one more rule is zeros if it is present between two non-zero digits, that will always be significant. Fine. So here we have this example 5.005. So these two zeros, they are in between two non-zero digit, which is 5 and 5, left hand side 5, right hand side 5. So you have to consider these two 0, and obviously the 2 5 we have to consider because it is non-zero. So total it is 4 significant figure. And finally, one more point, if there is any exact number, suppose there is no decimal. Sometimes what we do, suppose you are counting anything. So to count, we use exact numbers. Now, these exact numbers that are used to count, not measure. Try to understand the difference. We are using these numbers to count. Our purpose is not to measure. Then it will always have infinite significant figure. Now, just remember this last point that are mentioned in the first box. So this point, it is mentioned here when uncertainty is very high, then significant figure is very low. But if significant figure is infinite, that means uncertainty is 0. So when it is exact number, you know exact value, then obviously there is no question of uncertainty. And significant figure is, that is why it is infinite. So just take this example. Here we have picture of 4 apples. So it is exact. There is no question of measurement. And we know that when it is 1 meter, obviously it is 100 centimeter. Again, it is exact. When it is pound, it is actually 6 ounce. It is that is exact. Similarly, you can say when it is 1 kg, it is actually 1000 gram. It is not that 1000 point something like that. So it is exact. Similarly, from the picture you can understand there are 8 eggs. So that is why for these type of exact numbers which we are using for just counting purpose, not measurement purpose, in that case there is no question of uncertainty. And when there is no question of uncertainty, obviously infinite will be the significant figure. Okay. Some examples. 10082. So here these two zeros in between 1 and 82, it will be considered as significant. So it is 5 significant figures, that is all these 5 digits. Then 70000, it is basically 70,000. Now here only these 7 will be considered. That is the first digit 7, that is significant. So that is why here significant figure is simply 1. When it is 0.0025, this type of example we have already seen. There is 0 after decimal, but it is preceding 25. So that is why these two will not be considered. So here these two significant figure, it is only for the numbers 2 and 5. Similar is also for the next one. This 309 is basically these 3 significant figures, not the zeros. Come to the next one. Here we have 50010 decimal and then 3 zeros. So these 3 zeros are now significant because they are coming after decimal and also in the right hand side of this number 50010. So that is why it is considered, that is all these numbers are considered as significant. So it is 8. Now 0.004030. So only this part will be considered. So you can find similarity with these two examples. They are same type. Here also only 85 to significant for this type of number, which you can find similarity with the first example 10082. Here also it is all the digits you have to consider. Now these three are very interesting. You can they are very close to each other, but still there is difference in the position of the decimal. It is 7.00, then it is a number 700, then 700, but there is a decimal. So once you put a decimal here, now these two zeros, it will be considered as significant. But here when there is no decimal, then these two are not considered. Only 7 is considered. And for these two also, which is coming after decimal, it is also 3. 83.90, all the digits are considered. Here we have to consider only 85600. This is not considered. Only 8 and 9, so it is 2, then 9. So 4 here before decimal, 5 after decimal. Then we have a number which is expressed in this way, 6.2300. Now it is multiplied by 10 to the power minus 4. So if you write it without this 10 to the power exponent, it will be 0.00062300. So here it is mentioned that significant figure is 5. So how we are getting this? So you can find similarity of this number with this one, right? So these zeros are not considered, which are before 6. It is preceding 6. So only 62300, these 5 will be considered. So that is why 5 is the significant figure. 37.300. Here also all the numbers, all the positions we have to consider. It is 5. Then 33 point, total 5 zeros. Now these will also be considered. So you have to consider all of these. It will be 7. The first one is 5. Then we have 100 point. So we have already seen the example, which is 700. This one I'm talking about. Here you have seen it is 3. So this is also basically 3. But here when decimal is not present, it will be only 1. So 5, 7, then the next one 3, then it is 1, 302 000. This is also 3. Only these 3 will be considered. And here 1.050. This is also 3. Okay. 105. These 3 will be considered. So here it is 5731. Then 5731. This is 3. And write it freshly. Rounding of the numerical results. Sometimes the result that we get, there is a need to round off. You can also see in some integer type of question, it is mentioned in the question as instruction that round off up to this decimal like this. So when a number is rounded off, what it means actually, the number of significant figures that will be now reduced. The last digit retained is increased by 1 only. So what we do, if it is mentioned, suppose rounding off up to 1 decimal, that is after decimal, there should be only one number. Now these are the actual results, 12.696. But after 12, there will be only one digit. So we have to reduce these numbers. Now how to do so? If the last digit that is retained, so this is the last digit which is retained, that means the position 6 after 12, that part is retained. Now after 6 we have the number 9. So it will be 6 will be increased by 1 only if the next digit, that is the following digit, in our case the following digit is 9. So if the following digit is greater than or equal to 5, then you have to add plus 1 to 6. In this case it is 6, so it will become 12.7. Similarly, there will be no change, it will be left as it is if it is lesser than 4 or equal to 4. So basically when I am saying that you just add 1 when it is equal to or greater than 5, automatically it means you don't have to do anything, just keep it as it is if it is lesser than or equal to 4. So 18.35, in this case, if we want to write up to this position, the number 3 will be increased by 1 because the next digit is 5. So just look at this condition. If it is equal to 5 or greater than 5, in both cases you have to add it. So it is 18.4. But the third example, now if you want to write up to this, after 9 the next number is 3, which is obviously lesser than 4. That is any of these condition you can choose. It actually they mean same thing. So now you can write it as 13.9. These 3, it has no significance because it is lesser than 5 and not it is even equal to 5. So that is why it is left as it is. In this way we can round up these numerical results. Precision and accuracy. So when we do measurement, these two terms, they become very significant. Okay, look at these 4 pictures. In these 4 pictures, the middle point that you are seeing, that is actually the true value that we want to measure. Now if it is the true value, and suppose you have done the experiment 5 to 6 times, so all these 5 to 6 times you have obtained some results. Now all these results that you have obtained in these 5 or 6 times, if they are very close to each other, which you can see all these are at the same place, that is overlapped or merged, so it means they are precise. So all the 5 to 6 times the measurement that you have obtained, these values, they are very close to each other, but they are far from the actual value. So in this case you will say it is precise but it is not accurate, it is far from accuracy. Come to the second picture. Now among these 5 or 6, only one is very close to the true value, but if you individually see all these 6 measurement values, they are also far from each other, they are not overlapping to each other, their individual values are not close to each other. So it is not precise, but they are very close to the center, that is they are very close to the true value. In the previous picture, suppose if it is picture number 1, this is picture number 2. So in the first case, all these values, it is true they are close to each other, but all of them are far from the true value. But now they are very close to true value, so that is why they are accurate, but they are not precise. And the third possibility, they are not accurate, they are not precise, because if you look individually, they are far from each other, and also even they are only this one is close to true value, but others are not close to true value. And the last one, they are merging with each other, and also they are just on the true value. So that means they're precise as well as they are accurate. So precision means it refers to the closeness of the set of values obtained from identical measurement of a quantity. So you are doing the experiment several times, all the times the values that you are getting, if they are close to each other, it will be precise. Okay, so that is the reason in these 2 pictures, that is picture number 4 and picture number 1, these 2 are basically precise. Precision is simply a measure of reproducibility of an experiment. That means reproducible means what? You can produce the same result again and again. So that is why, though you are doing the experiment 3 to 4 times, but each time you are getting the value which are very close to each other. That means you can reproduce the value. So that is why it is all about reproducibility. And how you can obtain them? Precision is actually equal to individual value minus arithmetic mean value. So here the 6 results that you have obtained, you have to take the arithmetic mean and then This mean you have to subtract from this individual value. So you will get the precision. Accuracy. Accuracy is the agreement of a particular value to the true value. So now how far it is from the true value, that is important. So it is a measure of the difference between the experimental or the mean value of a set of measurement and the true value. So now what you will do, you will take the mean of all the results that you have obtained, you have to subtract it from true value, and that is actually the accuracy. But remember, in general what happens in physical measurement, it is mostly observed that accurate results when you are getting, it is always precise. So whenever you are getting some accurate results, that means the results are very close to the true value. So it is chances high that it will be precise also, but the reverse is not true. That means if you have obtained some precise results, suppose each time the values that you have obtained, they are very close to each other, but that doesn't guarantee that it will also be accurate. That means they will be close to the true value. That is not necessary. So that is why accurate results are generally precise, but the reverse is not true. We have a problem here which is related to significant figure. Using the rules of significant figures, here an expression is given. You have to find the correct answer for that expression. Here if we write 0.0285, it is multiplied by 0.112, and then it is divided by 0.5702. Okay, now when you will do this calculation, you will get the value. You can write as long as you want to write. Fine. Now here the rule that you have to maintain. If you look at this value, it seems as if the first, that is option A, is correct, but that is not necessary. Individually, if you see how many terms are given here, total 3 terms are given. This is number 1, this is number 2, this is number 3. Now you have to first check the terms that are already given in the question. You have to look at them carefully. So the reported answer, it should not be more precise than the least precise term in the calculation. Now in the calculation, you have total 3 terms. Among these 3, you have to find which one least precise. If you look at this, the first term, that is 0.02858. In this case, you have 4 significant figures. Come to the second term, you have 3 significant figures. It is 3, it is 4, and this one is also 4. So which one is least precise? This one is least precise. Now the final result that you have obtained from this expression, it should not be more precise than the least precise. That means the final result, it should have maximum 3 significant figures, not more than that, according to this condition. So if it is true, you cannot choose option A, because in this case you have total 4 significant figures. If you look at option 3, you have 3 significant figures, option C 2, and here it is 1. That means you have to choose option B. If you choose option A, it is greater than the least precise term in the calculation. If it is C, then you are taking more, that is lesser value. Actually you should take 3. Though it is mentioned it should not be more precise. That means the next value you have to take. So don't take 2 or 1, you have to take 3. So correct option is option B. Next topic is dimensional analysis. Sometimes it is required when we are doing some calculation. There is a need to convert units from one system to another. This is very common. You have to do it again and again. Now this method actually used to accomplish this, and it is known as not just dimensional analysis, some other names also we can use, factor level method or unit factor method. It is not very something very complicated, it is very simple. So what we do here, the information that you are seeking, that is information sought, that is actually equal to the information which is already given multiplied by the conversion factor. So information given, it is already given in the question. You just have to know what is the conversion factor. So now we will see some examples. So here we have length, mass and temperature. So there, if you look at these three, all these units, they are actually basic unit. It is not derived unit. Fine. So all are in SI. So SI unit meter. Okay. Now 1 kilometer, if we want to know it is in terms of meter, what is the value, then it is 0.62137. Similarly, when it is 1 meter, it is 5280 feet. Okay. Or it is 1.6093 kilometer. Fine. Now in this way, if you look at these values, they are actually conversion factor. Now just take for the mass, if it is actually L. So 1 mu, that is atomic mass unit, it is equal to, in terms of gram, the value is given 1.66 10 to the power minus 24. So if it is, that is the value in gram for 1 atomic mass unit. Now if it is suppose 5 atomic mass unit, so what we have to do? Now this number must be multiplied by 5. That means this, look at this, information sort, information given into conversion factor. That means here 5 AMU, it is the information given, and when you are multiplying it with it 1.66 10 to the power minus 24 gram, that means this will be the conversion factor. Similarly, if it is 1 inch, which is in terms of centimeter 2.54 centimeter, that means 2 inch, that will be, that should be multiplied by 2.54. That means 2 inch in the information given, and 2.54, that is actually the conversion factor. So here conversion factors are mentioned here, right? Sorry, it is a mile, it is not meter. Meter is only M, and MI is, it will be miles. So in this way, if you look at temperature, we mostly use the units Kelvin or degree centigrade, and 0 Kelvin is equal to minus 273.150 degree centigrade, 0.15 degree centigrade. And in terms of Fahrenheit, though it is not used frequently, not so common, Kelvin and degree centigrade is most common. But if you want to convert to degree centigrade or Fahrenheit, you have to follow these rules. Similarly, Kelvin and degree centigrade, these two are related to by this relationship. Okay, so this conversion factor we have to use. So next we will see some derived unit: energy, pressure and volume. So energy we use mostly joule. Now 1 joule in terms of calorie is 0.239. So if I say if it is 10 joule, that means 10 should be multiplied by 0.239. Then only you can get the value in calorie. And the opposite one is also given. 1 calorie is equal to 4.184 or 4.2 joule. So 4 calorie, that will be equal to 4 into 4.2. So 4.2 is the conversion factor and 4 is the information given. In this way you can get the information which you are trying to find. Then we have pressure unit, Pascal, ATM and bar, and their relationship to each other, that is also given. And all these are derived unit because see, if you break joule, it is actually involving kg, meter and also second. Similarly for volume, it is 3 times of the, that is you have to multiply the length unit, which is meter. So when it is 3 times, it will be meter cube. Now meter cube, directly you can write liter. So 1 liter, that will be 1 decimeter cube, but in terms of meter it is 10 to the power minus 3. So in this way, 1 inch how it is related to centimeter, centimeter how it is related to ml, milliliter, all these are given here. So from this table you can take this conversion factor which will be required for calculation. So using this conversion factor, we will solve this. What is the mass that you have to find in gram unit? What is the mass of an aluminium block? So obviously there will be height, width, all these things. So three values are given. Fine. Now 2, 3, 4 all are in which unit? In inches. But you have to find the mass in terms of gram. Some other informations are given. Density is given 2.7 gram per centimeter cube. Remember, density is mass by volume, right? And 1 inch for conversion, you have to use this conversion factor, which is 2.54 centimeter. So 1 inch is equal to 2.54 centimeter. That means 1 is equal to 2.54 centimeter per inch. So when we will find this mass, basically we will multiply the volume with density. Okay. Now density is given in terms of gram per centimeter cube, but volume, when you multiply all these three, you will get inch to the power 3. But that you have to convert to centimeter. Then only the unit of density and unit of volume will match, right? So that is why the calculation will be like this. So we already know that 1 inch is equal to 2.54 centimeter. That means 1 is equal to 2.54 centimeter per inch, or the opposite one also you can say. But you don't have to bother about all this. Just look at the calculation. Required mass, which we have to find in terms of gram, that you have to keep in mind. So this part, which is already given in the question, when you are multiplying it, simply it will be 2 into 3, 6, 6 into 4, it is 24. So it is 24 inch cube, but you have to convert it to centimeter. So all these terms individually, it should be multiplied by 2.54. So 2.54 should be multiplied 3 times for each value of these 3. Now once you do so, this total part is basically volume, and which will be having unit centimeter cube. Now if it is volume, according to the relationship, we know that mass is equal to density into volume. That means volume you have already obtained. Now you have to simply multiply it with density. Now density unit is gram per centimeter cube. So these two will be cancelled. Ultimately left is gram. So the final value that you are getting, it is 1.1 into 10 to the 3. Okay. So in this way we can use the conversion factor. Next problem is convert 1 joule into arc. So this is energy unit, but this is in terms of SI. This is in terms of CGS. So 1 joule, first you have to break it in terms of kg, meter and second, because it is derived unit. So joule is unit of work, and work is equal to basically force into constant. That means for force, the SI unit is, for force the SI unit is kg into meter into per second square. And for distance, the unit is simply meter. So when you multiply force and distance, what you get? You get kg into meter square into per second square, because it is kg meter second per second square. Another m is also there, so that is why now it is square. Okay. So kg you will convert it to gram, because ultimately it should be in terms of CGS unit, because it is arc. So kg should be converted to gram. 1 kg is 1000 gram. Meter should be converted to centimeter, but it is, remember, it is meter square. So 100 you have to multiply, that is, it will be 2 times. So 100 into 100, that means it is 10,000. So now kg you will write 1000 gram. In place of meter square you will write 10,000, and second square it is same for both joule and arc. Don't have to change anything. So it is 10 to the power 3. This is 10 to the power 4. It will be 10 to the power 7. And again see, it is gram into centimeter square per second square. The same format that you have followed in case of SI. kg into meter square into per second square. But now it is gram into centimeter square per second square. and ultimately these three together, force is gram into centimeter into per second square, and the distance is simply centimeter. So if you multiply it, you get arc. So this is the final result. 1 joule is equal to 10 to the power 7 arc. Okay. Now there are different laws of chemical combinations. So these laws are basically used when different elements, they, or sometimes it may be compound also, they are combining with each other and they are forming some compounds. So they follow some basic rules. So these rules are actually these laws of chemical combination. Okay. So look at this. Here we have total 6 laws. Though the first 4 laws are basically laws of chemical combinations, in which here they are actually these laws are made, that is also mentioned. The last two, they are not directly called as laws of chemical combination, but they are also related to the first 4, that is they are also equally important. Okay, so after finishing the discussion of the first 4, then we'll discuss these two, which is basically related to volume. Fine. Now here the first 4 that you are seeing: law of conservation of mass, definite proportion, multiple proportion, reciprocal proportion. Out of these 4, it is observed that for 2, 3 and 4, that means definite, multiple, reciprocal, for these 3, it is observed that there is a common limitation for all these 3, not the first one or 5 or 6. So what is the common limitation? They do not hold good. That means they are no longer applicable when same compound is obtained, but by using different isotope. So see, we know water chemical formula H2O, but if you take the isotope of hydrogen, we know there are 3 isotopes: hydrogen, deuterium, tritium. So instead of taking this isotope, if you take deuterium isotope, now the chemical formula, it should be like this: D2O. So both are actually water. Only difference is isotope of hydrogen is different. So compound is same, but you are using different isotope. And we know when it is different isotope, the mass is actually different. In this case, we consider the mass 1, but for D, we consider it 2. So there will be error in calculation. So for these cases, that is this particular case, when you are using some isotope, we can find some common limitation that these 3 laws are no longer applicable. Okay. The first law, law of conservation of mass. So as the name suggests, matter cannot be created nor destroyed in a chemical reaction. So not just chemical reaction, in physical change also you will observe the same thing. For any chemical change, total mass of active reactants, they are always equal to the mass of the product form. Now, based on the data Lavoisier obtained after carefully studying numerous combustion reaction is basically means reaction with oxygen, and if it is hydrocarbon reacting with oxygen, products are carbon dioxide and water. So it is observed from these different combustion reaction that in all physical and chemical changes there is no net change in mass. So mass will remain same after reaction, before reaction. It is a derivation of Dalton's atomic theory. Though this theory we have not discussed yet, it will be discussed, but it is basically as if derived from Dalton's atomic theory, because in Dalton's atomic theory the same thing is mentioned, that atoms neither be created nor destroyed. You can find some similarity. When this will be actually discussed, it will be more clear to you. Right now, just remember it is a derivation of Dalton's atomic theory, which says that atoms neither be created nor destroyed. Atoms neither be created nor destroyed. So total masses of reactants, total masses of products, plus masses of unreacted reactants. So it may happen sometimes that all the reactants are not converted to product. In that case, it will be total mass of product as well as the amount of starting material or reactant which is left unused, that is unreacted. Now there is exception to this law, that is you can say as if it is a limitation. You cannot apply this law for nuclear reaction. For chemical reaction it is fine, because when it is chemical reaction, basically the electrons that are surrounding the nucleus, only those electrons are involved in reaction. But when it is nuclear reaction, as the name suggests, now the nucleus of the atom is also taking part, and nucleus, when it is taking part, obviously now the law is not applicable, because in this case the mass is converted to energy. So whether mass is same or not, that may not match always, because if some amount of mass is converted to energy by this formula equal to mc square, c is velocity of light, e is energy, m is mass. So if m amount of mass is converted to energy, this will be the value of energy. Okay, so when this happens, now this law of conservation of mass is no longer applicable, because now you cannot match the mass before and after reaction, because some amount of mass is already converted to energy, and energy you are not considered. So that is why there will be error. You will not see that the value of total mass before and after reaction is same. No, it will not be so. So this is the only exception. So here we have this physical change. Water from solid form ice, when we are providing heat, it will be converted to liquid form. So this is physical change. So whether it is solid form or liquid form, it doesn't matter. Total mass will be same before and after the physical change. Next example, we have here chemical reaction between sodium chloride and silver nitrate. So sodium chloride and silver nitrate, it is producing sodium chloride and silver nitrate. Now it is producing sodium nitrate and silver chloride precipitate. Total mass of reactant, if we look at the left hand side, 23 into 1, which is for sodium, 35.5 into 1, which is for chlorine. And for AgNO3, this is the mass of 1 Ag atom, 108. Then 14 into N, 1, which is for nitrogen, and this part is for oxygen. Okay, so if you add all this, you will get 225, 28.5. And now look at the product side. We have sodium, so 23.1. We have 1 nitrogen, so this is 14 into N, 14 into 1. And for 3 oxygen, 3 into 16. For each oxygen, it is 16. And AgCl precipitate, this is for Ag, this is for chlorine. So again, we are getting same value. So it proves that matter is same, that is mass is same. So we can say matter cannot be created nor destroyed when some chemical reaction is involved. Okay. Here we have a problem which is based on law of conservation of mass. X gram of potassium chlorate. Potassium chlorate is KClO3. When it is decomposed by application of heat, it will be converted to KCl plus O2. If you balance this equation, it will be 2 KClO3, 2 KCl, 3 O2. This is the balanced equation. It is saying that X gram of potassium chlorate. So this is X gram. On decomposition, it is producing 1.9 gram of oxygen and 2.9 gram of potassium chloride. So these two are the mass of the products. Two products are there, potassium chloride and oxygen. We have to find the value of X. So as we know, before and after reaction mass is same, and it is a balanced equation. That is the number of all the atoms, number of potassium, number of chlorine, oxygen. Before and after reaction it is same. See, 2 potassium, after reaction 2 potassium, 2 chlorine, after reaction 2 chlorine. Here we have 6 oxygen atom, after reaction also it is 6 oxygen. So it is balanced both sides. So X you can easily get if you simply add these two values, 2.9 plus 1.9. So it will be X equal to 2.9, 1.9. Okay, so this will be the value. gram. Next question. 4.2 gram sodium bicarbonate. It is added to a solution of acetic acid, which is weighing 10 gram. So basically you are doing the reaction 10 gram acetic acid, 4.2 gram sodium bicarbonate. This is acid-base reaction. Sodium bicarbonate is base, acetic acid is acid. And what we are observing, it is observed that 2.2 gram of carbon dioxide is released. So one of the product is CO2. And there is also some residue. It is not clearly mentioned in the question what are the actual products. It is simply mentioned one of the product is CO2 and rest of the part is mentioned as if it is a residue. And the mass of this residue, what is present in the residue, that is not mentioned, but it is mentioned except CO2, the rest of the products, or there may be any unreacted starting material. So this residue is having weight 12 gram. Show that these observations are in agreement with the law of conservation of mass. So from this you have to prove that this law is obeyed. Okay. So this is the reaction between bicarbonate and acetic acid. This is product and this is rest of the part. So mass of reactant as it is given, 4.2 is the mass of sodium bicarbonate. 10 gram is the mass of acetic acid. If you add it, it is 14.2. Now mass of products, the residue is having mass 12, carbon dioxide is having mass 2.2, that is already mentioned in the question. So just added this and you are getting same value. So it proves mass of reactants is equal to mass of products. In this way we can say these observations, they are in agreement with the law of conservation of mass. Next law, that is the second law. It is saying that a pure chemical compound obtained by different sources. So a particular chemical compound you can make in different ways. It is not necessary that there will be always a particular way. You can make it in different ways. 3 to 4 ways may be there. Now whatever is the method you are following, it always consists of same elements combined together in a fixed proportion by weight. So it is better we take some example. Here we are making carbon dioxide gas. How? By burning coke in air. Coke is carbon, solid carbon, physical state is mentioned in the bracket. You are heating coke with oxygen and air is mentioned, which is basically meaning the oxygen. So carbon is reacting with oxygen and you are getting carbon dioxide gas. Here, if we see the formula of carbon dioxide, 1 carbon atom, 2 oxygen atom. So their atomic ratio is 1:2. Now next method, again you are making CO2, but now the method is different. Now what you have done, you have taken calcium carbonate, which is also known as limestone. It is a solid, you are heating it, there is decomposition reaction, you are getting carbon dioxide gas and calcium oxide solid. But this is second method of carbon dioxide preparation. Here also look at this, same elements, that same element means carbon and oxygen, just like the previous reaction. Same element carbon and oxygen again combining together in a fixed proportion by weight. So here you can find the weight also, but atomic ratio is same, and when atomic ratio is same, that means this weight will also be same. So for 1 carbon atom it is 12, for 2 oxygen it is 16 into 2, that means it is 32. So for the first case it is 16 is to 32, for the second case also it is 12 is to 32. So that is same for both. So that is why it is following law of definite proportion. Now the third method is we are doing a reaction between dilute hydrochloric acid and washing soda, which is sodium carbonate. So this is acid-base reaction. This is a balanced equation. When sodium carbonate reacting with 2 HCl, there is production of NaCl, H2O, liquid, that is simply water, and carbon dioxide gas. So here also one of these product is CO2 gas. But they are same element, carbon and oxygen, Same atomic ratio, that means here also the mass ratio will be 12:32. Okay. So some more information for this law. This law is the basis for the study of stoichiometry in chemistry, because you will see each time when we are checking the stoichiometry, it is same. Okay, 12:32. The validity of this law has been confirmed by various experiments. So as in this case, you are seeing total 3 different types of reaction, but in all these cases you can produce carbon dioxide gas. But whatever method you are following, you are always getting same elements combining together in a fixed proportion by weight. This law, there is another name for this law, which is definite composition. So why you should know the other names? Because if you are getting any problem where definite proportion, this term is not used, instead definite composition is used or constant composition used, so you have to understand that that is actually another name of definite proportion. Okay, so it is also known as law of definite composition or law of constant composition. Okay, problem on this law. 6.488 gram of lead combined directly with 1.002 gram of oxygen. Lead means Pb. So Pb directly combining with O2. Pb directly combining with O2, and it is producing lead peroxide. Okay. Now, peroxide is basically oxide. We know it is O2 minus. Oxide is O2 negative charge. But when it is peroxide, it is basically 2 oxygen atom. Just remember hydrogen peroxide. If you remove the 2 hydrogen, it is O minus, single bond O minus. So 2 negative charges there. Okay. So it will produce lead peroxide. And if you consider 2 plus oxidation state, then this should be the formula, because these 2 negative charge, that will be balanced by the 2 positive charge of lead. Okay. So here we have taken 6.488 gram of lead and 1.022 gram of oxygen. So this is one way by which you are making lead peroxide. But lead oxide can also be produced by another method. Which method? If you are simply heating lead nitrate, then you are getting, that is lead peroxide is also produced by heating lead nitrate. So when you are heating lead nitrate, which is PbNO3 whole 2, PbNO3 whole 2, because per NO3 there is charge -1. So to balance 2 positive charge, the formula should be PbNO3 whole 2. Though here formula is not required, I am just writing it. So PbNO3 whole 2, when you are heating it, then also you are getting lead peroxide. It was found that the percentage of oxygen that is present in lead peroxide, which is obtained by heating lead nitrate, that is 13.38%. Use this data to illustrate the law of constant composition. So in the second method also, when you are heating it, you are getting PbO2. So in the second method, it is already mentioned that the amount of, that is the percentage of oxygen, is 13.38. So if somehow we can prove that in the first case also the oxygen percentage is 13.38, that means that law of constant composition or definite proportion is followed, right? So how we can do so? 6.488 gram of lead is combining with 1.002 gram of oxygen. So the total mass will be, simply add these two. So here what we have done, we have simply added these two numbers, because these two are the starting material. So this is the total mass of PbO2. So 7.490 gram of PbO2, we can say it contains 1.022 gram of oxygen. but we have to find percentage because we have to compare with this value. So 7.49 PbO2 contain 1.002 gram oxygen. So 100 gram of lead peroxide will contain, it will be 1.002 divided by 7.490 multiplied by 100. If you do this calculation, you will see you are getting this value 13.38, which is matching with this. It means that this law is obeyed. Okay. So there are some limitations for this law, though it is true that in the first slide where we have seen all the laws of chemical combination, there we have seen there is a common limitation which is regarding isotope, but this limitation is different. Common limitation we have already mentioned. The limitation that you are seeing now, it is only for law of definite proportion. This law is not true if different isotopes of elements are involved. So this is already mentioned in 2 to 3 slides before. Now the other limitation, which is also only for this particular law, this law is not applicable when there are possibilities of making 2 or more compounds from the same element. So take this example. Suppose we have ethanol. Ethanol is having formula C2H5OH, and suppose we have dimethyl ether, that means CH3O CH3. So in both cases the formula is same, right? C2H6O. That means carbon, hydrogen, oxygen, they are present in the same ratio. C2 means 12 into 2, 24. 6 hydrogen means for each hydrogen it is 1, so it is 6, and for 1 oxygen it is 16. See, if you simplify it, divide by 2, it will be 12:3:8. So this is the weight ratio, which is same for ethanol and dimethyl ether, but these two are completely different compound, isn't it? So that is why now this law is not applicable, because according to this law, this element, their weight ratio, it should be same. So that is fulfilled for both of them, but it is not same compound, right? So this is obviously a limitation. So remember, whenever there is a possibility of making 2 or more compounds from the same element, not just same element, their atomic ratio is also same. Atomic ratio is 2:6:1, and this is the weight ratio if you consider atomic mass. So remember, this is another limitation. The limitation of isotope that we already know, but this is a new limitation for this law. So other laws we will see in the next class. Today we are ending here. Thank you for listening.